This video, I'm going to do a few more examples solving nonlinear systems. So let's jump right into it. I'm going to solve the equation 2x plus y equals 5, along with x minus 1 squared plus y minus 2 squared equals 10. So first thing I'm going to do is just think about the form of the equations. The first one is a linear equation. The second one, we have a circle. So if we think about crossing a circle and a line, we could have up to two solutions. Of course, it could end up being that there's zero reals, or that we have just one, kind of that one, the tangent line where it just brushes off the side of the circle. If I look at this, I need to first determine, do I want to use substitution or elimination? And substitution is going to be the way to go on this one. To eliminate, well, right now, it's very challenging to eliminate because, yeah, I see an x and a y here and here, but those are inside some squares. I would have to square those out before I was able to eliminate. And then once I square it, well, then I have x squared terms, I have x terms. It's really going to be very challenging to eliminate. So I'm going to use substitution. And the first one is definitely going to be the easiest to solve for because we don't have those squares on them. And on top of that, the y, I believe, is a little bit easier to solve for because I just have to subtract that 2x over. We could also solve for the x. That would require us to subtract the y and then divide by the 2. I don't want to deal with fractions, so I've just chosen to solve for the y. Now that I have an equation for y, I'm going to go ahead and plug in x minus 1 squared plus 5 minus 2x minus 2 squared equals 10. At this point, before I go squaring, I'm going to simplify it. It's always easier to simplify than just go multiplying out first. Same thing that's true. Notice I didn't start by squaring this first equation out. It is generally easier to insert that other variable, simplify before you go squaring, right? So I'm going to simplify at this point. X minus 1 squared plus 3 minus 2x squared is equal to 10. You could also write this as a negative 2x plus 3, does not matter. And I'm going to square these out. So when I square the first one, remember, when we see this x minus 1 squared, that is not just saying x squared plus 1. What it is saying is it's saying take x minus 1 and multiply it by an x minus 1. We're going to have to FOIL this out. So we're going to get an x squared. A negative 1 times x is a negative x. Another one gives us a negative 2x. And then a 1 times 1 is 1. Remember, there's a shortcut for squaring these binomials. You square your first term, you square the last term, you multiply the 2 and double it to get the center term. So we get an x squared, negative 1x is a negative 2x, negative 1 times negative 1 is a positive 1. I'm going to do the same thing on the second one. So we're going to have the first term squared is a 9. Multiply the 2, 3 times a negative 2 is a negative 6x. Double it, it's going to give me a negative 12x. And then square the last term, negative 2x squared gives me a plus 4x squared. That will be equal to 10. I'll collect my like terms. I have a 5x squared. I have a negative 2 and a negative 12. That would be a negative 14x. And then I have a 1 and 9. That's going to be a plus 10. And there is a 10 on the other side as well. It is a quadratic, so I need to get it set equal to 0. That means I'm going to have to subtract the 10 over. When I subtract the 10, I'm left with just a 0. Now that I have it equal to 0, I can factor. So I'm going to factor off the x. And I have left a 5x minus 14. I set both my factors equal to 0. And so I get x is equal to 0 and x is equal to 14 over 5. Well, now that I have those two x values, I'm going to plug them back into my y equals equation. I'm going to come back up to the top of the screen just so I can try to keep everything on one viewing window. So I'm going to plug in these two numbers. Well, y is equal to 5 minus 2 times 0, which is going to give me a 5. Second one, y is equal to 5 minus 2 times 14 over 5. Well, that will be y is equal to 5 minus 28 over 5. Getting a common denominator, this would be over 5. That would be a 25 over 5. So y would be equal to a negative 3 over 5. So we get a pair of solutions, 0, 5, and 14 fifths, negative 3 fifths. Two real solutions. We do remember how we started this problem off. We said if we cross a line in a circle, we could end up with two solutions, and we did. Let's move on to a second example. Here we've got the equations x squared plus y squared equals 4. Y minus x squared is equal to 5. We have a circle in the first case. In the second one, this is a quadratic. We have just the x being squared. So if we think about a circle and a quadratic, we could cross that up to 4 times. Now, it's definitely possible to cross less than that. So we could cross 2 times, or we could have 1 or 3, or we could in fact have 0 crossings, meaning zero real solutions. If we think about the best way to solve this one, well, we have a few different options, I think. I don't think it would be real hard to use substitution. Also notice that we do have similar variables kind of sitting on top of each other. The x squareds would cancel if we were to add these two equations. Maybe it would help if I rewrite this to really see that a little bit more clearly. Let's switch the order of these. I'm going to add the two equations, and notice the x squareds are going to cancel right away, and we'd have a y squared my goodness. This tablet is not a great piece of equipment. Y squared plus y is equal to 9. And so with just one step of elimination, we were able to get down to just y's. If you were to use substitution, it wouldn't be real hard either. You could have solved for the y. Y would be equal to x squared plus 5, and you could insert that into the other y. Now, the danger there is exactly what we saw a second ago, where you're going to have to take that and square it. You'd have x squared plus 5 squared equals 4. And that's going to end up meaning you have an x to the 4th term. And from there, you'd have to simplify and solve, right? So it's very doable. It's just getting to be really large powers. And so it is of quadratic form. Once you're to move everything to one side, you can solve it through, I think you're going to have to use quadratic formula. We can also solve for that x squared term, and we don't typically do that. We typically solve for just the variable x or y, but let me show you what we get. So we'd have x squared is equal to y minus 5. And the reason I can solve for the x squared here, notice in the other equation, we have x squared. That is what we need to replace with some version of y. And so when we do that, we'd have y minus 5 plus y squared equals 4. So like I said, normally we'd solve for the x. We get x is equal to plus or minus square root of 1 y minus 5. That's real messy with the plus and minus. But because we just have x squareds in the other equation, that is an option in this case. So that's another way we could do it. Notice once we get everything to one side, we get exactly the same thing we had over here in our elimination case. Now, I do think, again, elimination probably is the fastest way to go there, but we get to the same place. I think probably solving for y and plugging that in, that's probably actually the hardest in this case, rather than solving for the x squared or using elimination. So now I'm at the same point. I'm going to go ahead and solve this out. So I don't know how to factor this, y squared plus y minus 9. I don't know how to factor that, so I'm going to have to use a quadratic equation. So y would be equal to -1 plus or minus square root 1 squared minus 4 times the a times the c all over 2 times the a. I do a lot of simplification, so -1 plus or minus square root of 1 plus 36 would be 37 all over 2. These are rational numbers. They're not nice clean numbers, but they are sorry, they're not even rational. They're irrational. They are real. These are real numbers. They are not rational. We have a square root of the 37. So these are perfectly valid solutions. We can take these and we can plug them back into either equation. I think the second equation probably looks a little bit easier, or in this case, we had solved for the x squared. We want to know the x's. So I'm going to plug it back into this equation right here. X squared is equal to, let me start with the y is equal to -1 plus the square root of 37 over 2. So then our x squared equals -1 plus root 37 over 2 minus 5. I combine my like terms, so x squared is equal to -1/2 and 5 is -5.5 or -11/2 plus 37 over 2. And to get the x by itself, I'm going to have to take the square root. So x is equal to plus or minus square root of -11 plus square root of 37 over 2. Now, if we think about the square root of 37, that is a 6 and a little bit. It's less than 11, which means we are getting imaginary solutions here. They are solutions nonetheless. They are imaginary, but we would get plus or minus I square root of 11 minus 37 over 2. I'm just pulling that imaginary out. 11 minus square root of 37, that will be a positive. So I've pulled out that negative from both terms so that I can see that it is imaginary. So for that one y value, I'm getting two different x solutions. I'm going to have the solutions I square root of 11 minus root 37 over 2, comma, and then our y there was the negative 1 plus root 37 over 2. We also get the negative I square root of 11 minus 37 over 2, 1 plus or minus square root of 37, not plus or minus, just a plus over 2. So we're halfway there on the x's. I'm also going to take the y is equal to the negative 1 minus square root of 37 over 2. I'm going to do the exact same thing. So I'm going to plug x squared equals a negative 1 minus square root of 37 over 2 minus 5. Combining like terms, it's going to look exactly the same as what I have directly to the left, other than just the sign between the negative 11 and 37 is going to be a minus. I'm then going to take the square root, so x is equal to plus or minus square root of negative 11 minus the square root of 37. Those both were over 2, so I'm going to put it over that common denominator. I'm going to do the same trick of pulling out that negative as the imaginary number, because once again, it's definitely going to give us an imaginary number. They're both negative. I have 11 plus root 37 over 2. And so now we end up with our last two solutions. We have I root 11 plus root 37 over 2, comma, the y here was negative 1 minus square root of 37 over 2. And then the second one, we'll have the negative I square root 11 plus square root of 37 over 2, negative 1 minus root 37 over 2. So those would be our four solutions. Like I said, this one really, really ugly. We ended up with an irrational for the y, and then we ended up with an imaginary for the x. But the point I want to make is that we are doing the exact same processes, whether through elimination, saying, hey, we need to get rid of those like variables. In this case, x's are the ones that we can easily get rid of. The y is not quite the same. A y squared and a y not quite the same. So the x's, we can easily get rid of those through adding those two equations. We could have also substituted either the x's or y's. To substitute in y equals x squared plus 5, we ended up with this degree 4 polynomial. That's why we're going to end up with so many solutions right away. We're going to get these ugly imaginary numbers right away. And that's going to be kind of a pain, quite honestly, to plug back into to simplify to get those y's. We can do it, but it's going to be a little bit more work. That's why I think it would be easier if you're going to use substitution to substitute in the x squared equals y minus 5. But as we've seen time and time again with these systems of equations, substitution and elimination both available to us. One, probably easier, in my opinion, considerably easier, but both would work. And we get to the same answers. The answers aren't as pretty as some of the earlier problems that we've dealt with, but we get answers nonetheless. They are perfectly acceptable answers.